lab report for Physics 2211, Lab 4. The purpose of this lab is to observe the motion and change in energy of an object attached to a spring. The following equations will be important in understanding the motion. The change in energy according to the law of conservation of energy should always be zero. For this experiment, the energies present are kinetic, gravitational potential, and spring potential energy. Kinetic energy is equal to 1/2 mass times velocity squared. Gravitational potential energy is equal to mass times the gravity constant on Earth times the height. Potential spring energy is equal to 1/2 the spring constant times the displacement squared. First, I began analyzing the video of the motion using Tracker. I placed the origin at the top of the spring. I then inserted a calibration stick for the length of the spring, which was given to be 0.7 meters. Next, I created a mass point for each of the frames of the motion. I was left with a table of the data as well as a graph of the motion. I saved the X and Y components of the data as a CSV file to be used later in our model. Using the starter code provided, I created a computational model to predict the motion of the object and compare it to the experimental data. I began inserting the initial conditions. The mass is 0.402 kilograms. The initial position in vector form is -0.125, -0.60. The object starts from rest, so the initial velocity is 0. The time starts at 0, and I used a time step of 1/210. On Earth, the gravity constant is 9.8 meters per second. The spring constant was given to be 6.93. Using the spring constant and stretched length, I found L0 to be 0.123 meters. I specified L to be the position of the ball minus the position of the spring. I specified L hat to be L divided by the magnitude of L. I specified the change in length to be the magnitude of L minus L0. I then inserted equations to continually update the net forces. The only forces acting on the objects are gravity and the spring force. Using Newton's second law, I updated the velocity and position. Finally, I inserted the equations for each type of energy and the changes in energies. When I run the code, it produces a model of the predicted motion and the experimental data. The red ball indicates the experimental data, while the blue ball shows the predicted motion. The simulation produces a graph comparing the X and Y coordinates of the model and the experimental data. The X values are fairly close, but I suspect the Y values were skewed by the low precision of my tracker data due to camera quality and human error. And finally, we have the graph of the changes in energy. As you can see here, the change in total energy is almost exactly zero due to the conservation of energy. Some energy may be lost to air resistance, so it's not exactly zero. We are asked whether the energy principle is satisfied by our model. The answer is yes, because the total change in energy is basically zero, meaning no energy was created or destroyed. Next, we are asked to create two estimates of oscillation periods using the X position and the Y positions. Using the X position graph, the object oscillates through 5 periods in 8 seconds for an average of 1.6 seconds. Using the Y position, the object oscillates 6 periods in about 8.5 seconds for an average of 1.42 seconds. I think the Y period is shorter because the force of gravity causes the object to move faster in the Y direction. Thanks for watching. If you'd like to see my code, it's linked in the description of this video.